All right, so again, Newton gave us the laws of motion. He discovered gravity, the law of gravity, invented calculus, and so on. All right, so Newton's first law says the following. Here's an air hockey table. The layer of air, what it does is it eliminates friction between the puck and the table. So for instance, here's an object. If I push this object, that thing stopped. Why did it stop? So let me push this again across the table. That thing stopped. Why did it stop? Friction forces were acting in the opposite direction and they stopped it. And you see, if I push it this way, it'll stop again. Friction forces act always against the direction of motion. If you do that on an air hockey table, you push this puck, it won't stop. That's because you've eliminated friction. Okay? And that's what Newton's first law says. If an object is moving, and if no force acts on it, it'll keep moving. It'll maintain a constant velocity. Okay? And if it was at rest, it'll remain at rest if there's no forces acting on it. So to get it moving, to change its motion, you have to apply force. Okay? So now, so you needed an air hockey table to illustrate the fact that if it was moving, eliminating friction on Earth is hard. Okay, you don't see too many examples of that. But for example, if you went into space and threw a baseball, that baseball would keep going forever if it was not around any large body attracting it. Okay? So that's Newton's first law. So Newton's first law is if no force acts on it, its velocity will remain constant. Okay? And meaning if it was at rest, it'll remain at rest, and if it's moving, it'll maintain its constant velocity. Okay? Well, what does Newton's second law says? It'll say something about when the force is not zero. Okay? So when the force is not zero, then the object will accelerate. Okay? So if this is not zero, that won't be zero. So, and when it accelerates, its velocity changes. Okay? So when the force is not zero, velocity changes. Okay? So the object will accelerate, implying the object will accelerate. All right, so that's Newton's second law. Now the units of this are, we will deal with mostly SI units. Mass is measured in kilograms. Okay. Acceleration in meters per second square. So the units for force would be kilograms, meters per second square. Okay. And in physics, when you have a combination of units, okay, you give this a name in honor of a scientist that's worked in that field. Okay. So this combination of units is called a Newton, in honor of Isaac Newton. Okay. So the units of force are newtons, okay, the SI units of force. Now, in everyday life, we use pounds. Okay, so pounds are commonly used here, and that's a unit of force as well. Okay. So the unit of mass in these units is slugs, and unit of acceleration is feet per second square. But we'll mostly stick to SI units.
Excuse me.
Yep.
When you wrote in red, is that kilograms?
That's kilograms, meters per second square.
Thank you.
Yep. Newton's third law. So essentially, okay, it says whenever two objects interact, okay, so if this person exerts a force on the wall exerts an equal and opposite force. on the object. Okay, so essentially all forces come in pairs. Okay, and whenever two objects interact, the forces are equal and opposite. Okay, so for instance, we'll come to, okay, so let's say this is the Earth, and if your weight is 150 pounds, what does that mean? That the Earth is attracting you with a force of 150 pounds. So what does that mean? What does Newton's third law says? That means you're attracting Earth with a force of 150 pounds. Okay? So that's Newton's third law. For every action, there's an equal and opposite reaction. Okay? All right. So for instance, that's how you walk. When you walk, you're pushing against the ground, and the ground is pushing you forward. Okay? Yeah. So if your foot slips, for instance, then you're not applying if you are on a perfectly slippery surface, then you can't apply a force on the floor, and the floor can't push you forward. Okay? So for every action, there's an equal and opposite reaction, and that's Newton's third law. Okay, so there will be situations you encounter when several forces act on an object, and we use the superposition principle then. Okay, so for instance, on this person, if there are two forces acting, that one and that one, the effect on this person is equivalent to the sum of these two forces. This force is that, and this force is that. The sum of these two forces is that. Okay, so the superposition principle says the motion of this person would be the same whether these two forces act on her, or just this one single force acts on her. Okay. So did you guys understand that? Let's say there are 10 forces acting on a person. Okay. So we'll apply 10 forces on her. And the second time around, we'll apply just one force, which is the sum of all the 10 forces. Just a second. We'll apply that single force, which is the sum of all the 10 forces. You can't tell the difference. Did you guys understand that? Okay. Okay, so that's the superposition principle. Question? Okay. All right, so whether you apply several forces or a single force, that's the sum of all the forces, the effect is the same. Okay? So what this statement is see, a force acting on an object of 1 kg, if you have a 1 kg mass, 1 kg is roughly 2.2 pounds, and it produces an acceleration of 1 meters per second square. If this is 1 kg and that's 1 meters per second square, the force acting on the object is 1 Newton. That's just a operational definition. Okay. All right, I'll show you one problem, and it's fairly easy. Okay. So this says, the problem says, a 440 gram can of food. Soda can is, nobody has a soda can. A soda can is about 360 grams. So this is a can of food. This is a slightly more. This is essentially 1 pound can of food. Okay. Is given a shove on a frictionless level surface and is observed to accelerate at 1.5 meters per second square. How much is the force in Newton applied by the shove? Okay, so this can is sitting on a frictionless surface. You're applying a force and you give it an acceleration. And you just saw from Newton's second law, force is mass times acceleration. The mass of the object is 440 grams. You have to convert that to kilograms, okay? And 1 kilogram is 1,000 grams. So that is the conversion factor. So when you convert units, see, you're converting this to kilograms. All you're doing is multiplying it by 1. You see that 1 kilogram is 1,000 grams. So if I divide this by that, that's like its unity. So 1 kg by 1,000 grams is 1. And you see you can multiply anything by 1. Okay? Anyway, so there's the conversion. This is 0.44 kgs. So the force you're applying is 0.44 kg times 1.5 meters per second squared. And 1.5, half of that is 0.22, and so that will be 0.66 newtons. Okay. So again, a fairly easy problem. Calculating a force is just mass times acceleration. Okay. Okay, Newton's law of gravitation states that every object in the universe attracts every other object in the universe. Okay. So let's say this is the Earth, and that's the moon. The Earth attracts the moon, and the moon in turn attracts the Earth, according to Newton's third law. Okay. The magnitude of this force is given by this formula. Okay. How strong the force is given by this formula. Okay. And this formula says, again, you don't have to memorize this formula. Like I said, what this formula says is there's a gravitational constant. M1 and M2 are the masses of the two objects. Okay. M1 is the mass of this, M2 is the mass. And R is the distance between the center of masses of those two objects. Okay. So the force of gravity between these two objects is proportional to the product of the masses and inversely proportional to the distance squared. So that's Newton's law of gravity. Gravity is the weakest of, there are 4 fundamental forces in nature, and gravity is the weakest. That's because this gravitational constant is very small. Okay? So, for instance, okay. So Earth attracts, and so if I jump off this table, chair, I'll fall towards Earth because the Earth is attracting. Right, she's attracting her. Why isn't she falling toward her? What?
The opposite direction.
They're not falling toward each other, right? So why is that? I'm sorry? Very good. The force is so small. Okay. The Earth attracted me with a force of 160 pounds. The force of attraction between these two people is roughly the weight of one of your hairs. Okay. So, and that force between them was so small because this constant is small, and if to have a large enough force, you need a large mass. And the Earth's mass was large, and so I was attracted. The Earth exerted a noticeable force on me. Okay. All right, so we want to understand 2 terms, gravitational force and weight. Okay. So for instance, here is the Earth, and here in North America, the force on me by the Earth is toward the center of the Earth. Okay, so if I went in Australia, there the force would be in that direction. that would be the force of gravity, and that's a vector. Okay? Vectors of magnitude and direction. Okay? But just the magnitude of the force is called your weight, which is just your mass times gravity. Okay? The magnitude is called the weight. Okay? So in kilograms, roughly the average weight around here is 50 to 60 kgs for us. Okay, so our mass is about, let's say, 50 kgs, and g, the acceleration due to gravity, is 9.8 meters per second square. So the average weight in this for us is 50 times 9.8 meters per second square. It's about 490 newtons, okay, or 500 newtons. That's our weight in this room. Okay. All right. So here is this person holding a laptop. Okay. The Earth is exerting a force on the laptop, and that's the force of gravity. Okay. And the reason this thing is not falling down is because this person's arm is exerting a normal force that's equal to the force of gravity. Okay. And that is called it's called a normal force because it's perpendicular to the surface to this interface. And that's the normal force that's balancing the weight of the laptop. Yep. So we'll encounter normal forces in many situations. When we talk about friction, that'll be important. Yep. And sometimes normal forces are represented like that as well. Yep. Okay, you want to understand the term tension. Okay. So here are two boxes connected by this rope. Okay. And this rope is under tension. Okay. So when you have a rope, think of a stretched rubber band. A stretched rubber band is under tension. Okay. So let's say this is under a tension of, so I say if this is under a tension of 15 pounds, what does that mean? What do you think that means? Okay, so when a rubber band is stretched, it wants to contract, it wants to shorten. If this rope is under a tension of 15 pounds, what that means is whatever is connected to the rope is exerting a force of 15 pounds. So the rope is exerting a force of 15 pounds on this box in that direction, and the rope is exerting a force of 15 pounds in this direction on this box. Okay, so that's what it means to say the rope is under tension of 15 pounds. Okay, so on this box, what are the forces? This tension, there's the weight of gravity, and there's the normal force. On this box, there are two forces acting, the weight of gravity and this tension. Okay. All right, so you have to remember you have to understand tension. Okay. All right, here's a barge, and there are several forces acting on the barge. There's this little tugboat pushing on the barge like that, this tugboat pushing on the barge, and there's friction between the barge and the water. Okay, so these tugboats are pushing, and the net effect is the barge is moving in this direction, and friction always acts in the opposite direction. So this is called a free body diagram. In a free body diagram, what you want to do is just show the essential features in the problem. Okay. So what have we done in this free body diagram? What this barge is represented by this point. Okay. So you can do this when the object is not spinning. So the object on which the forces are acting, that is represented by a point. This force is drawn there. This force is drawn there. And the friction force is drawn there. So there are three forces acting on the object. You can add these three forces, and there is the net force. The sum of these three forces is this net force. Okay? And this acceleration of the barge is given by that equation. Okay, so the acceleration will be the net force divided by the mass of the object. Okay? So that's how you solve problems. So in the free body diagram shows you just the essential features involved in the problem. Okay? All right, now we'll talk about friction forces. And like I said, friction is useful in many situations. It's a nuisance in other situations. Without friction, you couldn't drive, you couldn't walk, and so on. Okay. All right, so let me, okay, well, so, all right, so here's a box sitting on the floor. If the box moves in this direction, the friction force will act in that direction, and if the box moves in this direction, the friction force will act in the opposite direction. Okay. And the way friction arises is if you magnify these two surfaces, they're never smooth. They're bumpy like that, and if the box is trying to move in this direction, the bonds between the atoms of this surface and that surface are trying to pull it back. And as you move, you're having to break those bonds, and that's where the friction arises. Okay. All right, now let me show you a little app. Okay. All right, so if there was no friction, you just had to apply a little force and you can get it moving. Oops. Okay. Okay, so you see Newton's first law says if there was no friction, an object moving will keep moving. Okay. All right. So, and an object at rest will remain at rest. Okay, so let me reset this. Okay, now what we'll do is, so what I'm going to do is, there is friction now. There's friction, and let me push this box. Okay, so you see I have pushed this, I have applied a force of 50 newtons. I applied a force of 50 newtons, except that the box didn't move. That was because there was an equal friction up to it. A 50 Newton friction in the opposite direction, and the box didn't move. This is called a static friction force because the box is not moving. Okay. Now I've applied a force of 80 newtons, 81 newtons. The box still hasn't moved. Okay, so you can see that the static friction force can change. Okay. What is the static friction force now? 0. Okay. All right, so the static friction force can be anywhere from 0 to a maximum value. Okay. So the static friction forces are denoted by small f. The subscript tells you whether it's a static friction force or what. Okay. So the static friction force can be anywhere from 0 to a maximum value. Okay. And now we'll figure out what the maximum value is. So let's go back to that app. Okay, so for this guy, all right. So I'm going to apply a force, 36 newtons, 50 newtons. See, I'm looking at that. 65 newtons, 70, 93 newtons. It's still not moving. So we haven't reached maximum yet. 105, it's not moving. 120, nope. Okay, so it was somewhere between 120 and 130. Okay, it turns out that for that setting, the maximum friction force was 125 newtons. Okay. Now it turns out that once you get it moving, now there's still friction force. This friction force is called the kinetic friction force. Okay, and that is always smaller than the maximum static friction force. Okay. So, once the object is moving, that friction force is called kinetic friction force. And this is always smaller than the maximum static friction force. All right, what this formula gives you is the maximum static friction force. The maximum static friction force is mu s. This is called the coefficient of friction. Okay, and that just tells you how sticky two surfaces are. Okay, so for instance, if you took this object and put super glue on it and put it on the table, what you've done is you've increased mu. Okay, mu tells you how sticky two objects are. Okay, and I'll come to that in a second. So there's the maximum static friction force, and there's the kinetic friction force. So mu s is the stickiness, Fn is the normal force. So here's the weight of the object, and there's the normal force. Okay. Okay. So for instance, if you press down on this object, in addition to the weight, this force will increase. So this is the normal force. Okay. And the friction force is mu s times the normal force. And so both for static and kinetic friction force, the friction force is mu times the normal force. Okay. So this graph shows you there's the maximum static friction force, and the kinetic friction force is always smaller than the maximum static friction force. That's what this graph shows you. Okay. All right, so you see there's the stickiness, that's the static friction force, coefficient of static friction, and there's the coefficient of kinetic friction. This fellow is always bigger than him, so the maximum static friction force is always bigger than that, than the kinetic friction force. And this table shows you that. See, the static friction force for a rubber sitting on rubber on dry concrete, those are the surfaces. That's 1 and that's 0.7, and we'll come to these numbers in a second. Shoes on wood, 0.9 and 0.7. Okay. Rubber on wet concrete. Okay. See, on wet concrete, it's the static coefficient of friction is decreased. So for instance, on a rainy day, it's harder to stop your car. Okay, that's because the static coefficient of friction is decreased. Okay. All right, let me show what this means, this number means. Okay, so we'll do it for that guy. Okay, so let's say here's a block of rubber, 100-pound block of rubber sitting on concrete. The normal force will be 100 pound, okay, because this block is not going through the concrete. This weight is balanced by that. Okay. Now, if the object is moving in that direction, there's a kinetic friction force in the opposite direction. And the kinetic friction force is mu k times the normal force. Mu k is 0.7. And the normal force is 100 pounds, 70 pounds. Okay, so what this number means is to keep a 100-pound block of rubber moving on a concrete surface, you have to apply a force of 70 pounds. You have to apply a force of 70 pounds to balance that. Okay, that's what those numbers mean. Okay. So to keep a 100-pound block of rubber moving on wet concrete, all you need is 50 pounds, and so on. Okay. Again, I'm just showing you that you don't have to remember any of that stuff. Okay. So here is an application. So for instance, during a massage, the normal force increases if the massage therapist supports more of her weight with the massage. So for instance, okay, so let's say you want a deep tissue massage or stuff like that. So the masseur has to press down hard on you to reach deeper muscles, and the normal force is higher. Okay, so if the masseur wants to move their arm, their friction force is large. Okay, the friction force is large, and the friction force is mu k times the normal force. So to decrease the friction force, they have to decrease mu n, the coefficient of friction, and that's why they apply oil on your body. Okay, so while giving deep tissue massage, okay, they have to use oil. Okay. All right. So more overweight with this causes more friction because Fn is larger. To compensate, a lubricating oil with low coefficient of friction is used. All right, so now that we've learned about forces, let's apply them to some of the muscles in your body. Okay, so you have two kinds of muscles, flexor muscles and extensor muscles. Okay, so in muscles, oftentimes muscles are joined to two different bones, and then there's a joint in between. Okay, the way muscles apply forces are by contracting. That's the only way they can apply forces. Okay, so when this muscle contracts, it pulls on this bone, and these two bones come together. So this is a flexor muscle. This muscle is joined there, and when this muscle contracts, it extends your legs. So if the leg was bent like that, it'll extend like that. And this is called an extensor muscle. Okay. So they're doing two different things. Okay. So here's another example. Your bicep is attached to that bone and this bone across this joint. And when the bicep contracts, it'll bring this bone and that bone closer together. Okay. So that's a flexor muscle. And so when my bicep contracts, these arms came together. And when my tricep contracts, my arms extend. Okay? So those are the flexor, and that's the extensor muscles. Okay. All right, now in this diagram, these are the shoulder muscles. Okay. Now we'll answer the question, why do you have so many muscle fibers? Okay. Or why do we have so many muscles in the body? Anybody know why do we have so many muscles in the body? All right. Go ahead.
To move around.
I'm sorry?
To be able to move around.
Yeah, I mean, to be able to move around. But what the reason for so many muscles is that way you can apply forces in different directions. Okay, so that's what this diagram is showing you. So for instance, okay, let's say this muscle applies a force, that muscle applies that force, and if you want a force only in that direction, only that muscle will contract. Okay, if you want to apply a force in this direction, this has to contract, that has to contract, that has to contract, and the sum of all these forces is that. Did you guys understand that? So if you want a force only in this direction, only those two forces need to be applied. Okay? If you want a force in that direction, these four forces need to be applied. Okay? So there are hundreds of muscles in the human body, allowing forces to be exerted in almost any direction. Okay. Now, we talked about this in the introduction. The more muscles are involved, the less efficient you are. Okay. So, you guys remember what is the maximum efficiency of human body? 20%. Very good. Okay. And swimming on the surface is 2%. Remember? Okay. And so, when more and more muscles are involved, your efficiency goes down. Okay. There are sphincter muscles. So we talked about muscles that are connected to two different points in the body. There are sphincter muscles that are circular muscles, and they have a different function. They open and close openings. Okay, so when they contract, so for instance, okay, they join back on themselves and cause the constriction of openings when they contract. Sphincter muscles have several functions. So, for instance, in the esophagus, here's the sphincter muscle. It turns out that you will learn later, in the esophagus, the pressure is lower than the pressure in the stomach. Okay, and so if the pressure is lower, your stomach acid should flow back into the esophagus, and that is prevented by the sphincter muscles. Okay. So here's another example. Okay, so for instance, so there's the eye lens, and around the eye lens is a sphincter muscle that contracts the eye. Okay, so what the function of the lens is to have a image focused on the retina. So when you are looking at far away objects that are far away, this sphincter muscle is relaxed. Okay, these, you can think of these as rubber bands that are attached to the lens. They are stretched. The lens is thin, and your eyes are focusing far off objects on the retina. When you want to see a close object, the sphincter muscles contract. These nodules have become small. The lenses become thicker, and the close by objects are focused on the retina. Okay, so again.
First one, is it focused behind the retina or on the retina?
So, okay, so let me show this. Okay, if I want to see a far off object, the sphincter muscles are relaxed, the lenses become thin, and the far off object is focused on the retina. When I want to look at a close object, the sphincter muscle is contracted, the lens has become thicker, and now the image is focused on the retina. Okay? So your eye is pretty amazing, and it does this instantaneously. Okay?
Sorry, on the second one.
Just a second. This thing cannot change its focal length. The lens in your eye changes the focal length just like that. Did you guys understand that? And with the use of the sphincter muscles. Okay. Yep.
Okay, so it's still sounding like with the image is it focused on the retina or behind?
The goal is, if you want to see something, the image has to be focused on your retina. Okay. And when it's not focused on your retina, you have a problem. Okay. And that's why there are devices like these. Yeah. All right. Yep.
Does that also relate to like your pupil? So like when you're reflected to light, it constricts and gets bigger.
So the job of the pupil is, if it's too bright out, you don't want too much light falling on it,
Yeah.
so you constrict the pupil. Yeah. Okay. So the job of the pupil is to control it's the aperture in photography. Okay. Control the amount of light coming in. the job of focusing is the lens and the cornea. The lens does 25% of the focusing. Cornea does 75% of the focusing. All right. Now let's, now that we have learned about forces and stuff like that, let's see how to fix a few problems. Let's say this person's backbone is broken, and so what do muscles want to do? The muscles want to contract, okay? And if the muscles in the back contract, the bones, if they impinge on the spinal cord, they can damage the spinal cord, okay? So you have to keep the spinal cord stretched, okay, while the bones are healing. And here's how they do it. So, okay, so they put pins on the skull and they hang weights. And so the spinal column is under tension, holding it apart while the bones heal. Okay, so this is called a striker frame. Has anybody seen this? I'm sorry?
Yeah,
Okay. Nobody?
very old. In old ways.
Okay. Well, anyway, what you have to do is you have to keep the backbone stretched. So while the bone heals.
I haven't seen a striker frame, but I forget what it's called, but I have seen
Mhm.
another one of like the old technologies where like, you know,
Mhm.
back in the day, if you had your femur bone cracked in half, or you had to pull apart the leg.
And we'll
so
see that on the
femur
next.
wouldn't,
We'll see that on the next one.
impale you. Okay, cool,
Yeah.
yeah. So I have seen that, but I haven't seen the other
Okay.
one, striker. That's neat.
I wonder if that neck frame is doing the same job. On the striker frame, you got to lay on this thing forever, or till your bones heal. So maybe the neck frame nowadays do the same job. The neck.
I've seen that before, but they do like a cage around your head,
Mhm.
and then they put like weights on either side, like while you're laying down.
Mhm.
They're like lifting from like a thing going around your head.
Halo.
So you're laying down on this table,
Mhm.
and the weights are hanging from the frame.
Like the side of your head while you're laying down on the table.
Mhm.
There's like a cage thing around your head,
Mhm.
and then they have the weights on either side,
Okay.
on the side that your head's on.
Okay. Yeah. So it's essentially the same thing.
Yeah.
Okay. So anyway, the goal is, okay, so what is the problem you're trying to fix? Your muscles contract and they would bring broken bones together, which would cause damage, and you want to prevent that. And you're stretching whatever it is that you're stretching, okay? So that's the idea, okay? And here's another example. Okay, so here's a broken femur, and this is a strong muscle that would bring the femur and those broken bones together. And of course, then the bones wouldn't heal properly. And so how do you prevent that? Okay, this guy is just supporting the weight of this if your lower leg. And so to do this, you have to put pins in the bone here. You have to drill pins. And you have to pull on that bone to counteract the pull of the muscle. Okay. So there is another frame to counteract the contraction of the muscle so that your bone can heal properly. Okay. Do you guys understand that? Okay. Any questions on that? All right, so now we will learn a couple of things to learn how to lift properly. Okay, so we'll understand the term torques first. Okay, so if you apply a force to an object, it can accelerate an object. Forces can also rotate objects. So for instance, if I apply a force here and an equal and opposite force here, now instead of moving, the object will rotate. Okay. So the effectiveness of a force in making an object rotate is called the torque. Okay. And let's see how torques are calculated. So forces can cause linear motion and rotational motion. Okay. The effectiveness of a force in producing angular acceleration is called torque. So the effectiveness of, so just like linear acceleration, there is something called angular acceleration denoted by alpha. Okay. So just like force is mass times alpha, torque is moment of inertia times alpha. Okay. Don't worry about the formula, but so the effectiveness of a force in giving angular acceleration is called torque. Okay. So the efficacy of a force in causing rotational motion depends on its moment arm. So for instance, you use wrenches. Okay. So you apply a force, and what you want to do is you want to loosen the nut. And you guys probably all know this, the longer the wrench handle, the easier it is to open the bolt, loosen the bolt. Okay. So torque on the wrench is force times the lever arm. And the lever arm is this distance, the perpendicular distance. So in this case, there's the lever arm. In this case, there's the lever arm. In this case, there's the lever arm. Okay. So this force is applying the smallest torque. So the torque is force times lever arm. So this lever arm is small, this is bigger, and this is the largest lever arm. Okay. So the larger the lever arm, the greater the torque, and the easier it is to loosen the nut. Okay. So that's torque. Okay, again, different diagrams. Now you also understand why they put doorknobs as far from the hinge as possible. Okay. So you get the maximum lever arm and the greatest torque. Okay. Okay, this is just condition for equilibrium. So if you want an object to be at rest, okay, the net force on it must be 0. If you want this to be at rest, the net force on it must be 0. Okay, so but that condition is not enough. So for instance, here is this object. The net force on this is 0 because this cancels that. But here is another situation. The same object, you apply a force F in this direction and F in this direction. The net force is 0, but this object will spin. Okay, and that's because the net torque was not 0. So if you want this extended object to be at rest, you have to have two conditions. The net force needs to be 0 and the net torque needs to be 0. All right, so let's try and understand this problem. Okay, again, you just need to have a sense for this problem, and I'm going to walk you through this, and you'll learn an important fact. Okay, so here's this person holding up this book. Okay, so if I hold this book, if I hold this weight, what this weight is trying to do is rotate my arm like that. And my biceps are applying a force to prevent that. Okay? So when you hold a weight, your arm wants to rotate this way about that hinge point, and your muscles are preventing that. Okay? All right. So here is the weight you're holding. Here is the hinge point. This weight is trying to rotate your arm in this direction. The weight of the arm itself, there is the center of gravity of the arm, that's also rotating your arm in the around the hinge point. The force of the biceps is preventing that. So if you're holding an arm and you're at rest like that in equilibrium, the clockwise torques are being balanced by the counterclockwise torques. Clockwise torques are torques that are rotating the arm clockwise, and the counterclockwise torques are due to, the counterclockwise torque is due to this force. This force is trying to rotate your arm counterclockwise. So let's see what are the forces involved. Okay. And again, you just have to have a sense for this. But I'm going to walk you through the details. Okay. So this physics book is 4 kgs. Again, 4 kgs each. 1 kg is about 2.2 pounds. So maybe you want to remember that. Okay. So that's 4 kgs. The arm itself, the bone weighs about 2.5 kg. Okay. So what this is converting that mass into newtons. So mass times gravity is newtons. So the weight of the arm is 2.5 kgs. 2.5 kgs times 9.8, that's 25 newtons. The weight of the book is 4 kgs times that, that's about 40 newtons. Okay. So there's 40 newtons and 25 newtons. Okay. Torque is force times lever arm. That would be the lever arm. That's 40 centimeters. Okay. So there is the book, which is 39.2 newtons times 40 centimeters. Now, normally we would convert that to meters, and that would be 0.4 meters, but the author chose not to do it because he doesn't convert it for the clockwise torque, and so if you don't convert it for the counterclockwise torque, then that's fine. Okay, so the clockwise torque is that of the physics book times the lever arm. So the weight times the lever arm, that's what that term is, the weight times the lever arm. Okay. Plus the weight of the arm times that lever arm. That was 25 newtons, that weight was 25 newtons times the lever arm, 15 centimeters. So the torque that is trying to rotate your arms clockwise is this plus this, which is balanced by the force of the bicep, times that lever arm, which is 4 centimeters. Okay. Okay, these two forces are trying to rotate it clockwise. That force is trying to rotate it counterclockwise. All right, so if you multiply all this and divide that by 4 centimeters, the force that the bicep exerts is 484 newton, 500 newtons. All right, here's what I want you to notice. What is the weight of this book? 40 newtons. To lift a 40 Newton object, your bicep had to exert a force of 500 newtons, almost 12 times greater. And that's generally true. Okay? So in everything you do. Sounds like your body is very inefficient. To lift a 10-pound force, you're applying a 120-pound force. Okay? And that's because, your muscles apply forces by contracting. They're very strong, but they cannot contract too much. And that's the reason why it's like that. Okay? And not only that, the moment arm for your muscles is always very small. Okay? So your muscles apply a great force, and because their moment arms are small and the torque is small. Okay, so that's so I just want you to have a sense for that again. So the combined weight of the arm in the book is 63 newtons, 64 newtons, and yet the bicep applies a force of 480 newtons. That's a factor of 8. Okay, so you apply the force 8 times greater. Okay, and so this is the bicep is said to have a mechanical disadvantage. Okay, so mechanical advantage is defined as output force divided by input force. Okay, so in this case, the output force was 60 newtons, and the input force was 480 newtons. Okay, 480 newtons. So the mechanical advantage was 1/8. It really was a mechanical disadvantage. Okay? So the mechanical what that 1/8 number tells you is to lift 1 pound, you're applying a force of 8 pounds. Yep. All right. All right, well, let's talk about posture now that you are experts at torques and stuff like that. Yeah. All right, they tell you to stand erect. And, okay, so this is your upper torso. So here's a sort of a free body diagram. If the center of mass of your upper torso is right above the pivot point is your hip joint. If your center of mass is right above the pivot point, now none of your muscles have to apply any forces. Let's say you have an incorrect posture. You lean over forward. What is happening is your upper torso is trying to fall down, is trying to rotate this way. And so you have a clockwise torque about that point. And to balance that, your back muscles have to apply a counterclockwise torque. So if I walk around like that, my back muscles are always contracted. Okay. And you, in addition, you just saw that, you have a great mechanical disadvantage. To support 1 pound of weight, how large a force did you have to apply? I'm sorry? 8 pounds. I mean, my torso is more than a pound. It's probably about 60, 70 pounds. To support that, my back muscles have to work hard. Okay? So, this weight times this lever arm is balanced by the back muscles and that lever arm. Okay? So, again, you want an erect posture. Okay. All right. Now we'll show you the proper technique for lifting. If you lift like so, okay, so again, there is your pivot point. This weight times this weight plus your torso is trying to topple you over this way. And if you're lifting like this, it's your back muscles that are providing the counterclockwise torque, that are preventing you from toppling. So you're using your back muscles to lift this object when you lift like so. You don't want to do that. Okay. Here is how you lift with your legs. Okay. Now, if you lift like this, okay. Again, by the way, this weight has to be on this side of your knee joint. Okay. So that will provide the clockwise torque. And this is a strong muscle. That's what you want to use. So this muscle will apply a force in that direction about that pivot point, and that will provide the counterclockwise torque. So this is a clockwise torque trying to rotate around this joint in this direction, and this muscle will provide a counterclockwise torque. Okay. So what you want to do is, so when you ideally lift, you want to bend at your knee, and the weight should be just outside your knee, as close to the knee as possible. If it's inside the knee, then you can't lift the object. Okay? So you want to be just outside the knee, and then lift it up. And then you're using your leg muscles to lift. Okay? Did you guys understand that? Okay. So, all right, we'll learn one last thing. So now, so here's a glass of water, and let's say you throw a little dirt in it and mix it up. So there's dirt in this water. And this will apply to blood and cells in your blood. Okay. Now, if I let this glass sit, will that dirt settle to the bottom? Okay. So similarly, if you have blood, the blood cells in the blood will settle down. Okay? Do they settle fast? No. Okay. Why don't they settle fast? Is there any way to make it settle fast? You spin it around in a centrifuge. Okay, so they don't settle fast because the force of gravity, the acceleration due to gravity is small. Okay? Now, spinning it around makes this acceleration due to gravity bigger. Okay? Effectively. And you can increase it by a factor of 1,000,000 in centrifuges. And that's the idea of the centrifuge. Okay? And that's what we're going to try and understand. You guys understand where we're going? Okay. So what you're trying to do is effectively increase gravity by 1,000,000-fold. Okay. All right. So this seems unrelated, but here we go. So let's say you're driving on a circular road at constant speed. Okay, so here's your velocity there. There's the velocity there. So you're driving around at constant speed. Are you accelerating? Why are you accelerating? The speed is constant. Very good. Thank you. You guys listened. So the direction is changing and the acceleration is pointing toward the center. This acceleration is the subscript C telling you it's centripetal acceleration. And it's called centripetal acceleration because it's pointing toward the center of the circle. Okay? And the centripetal acceleration is equal to the speed square divided by the radius of the circle. Okay, so that's the centripetal acceleration. And now you can see that the faster you go, the greater the centripetal acceleration. Okay? And that's what the idea of the centrifuge is, you know. So in a centrifuge, you have a circle like this, you put blood in a tube like that, and it spins like crazy. Okay? And so the so the acceleration toward the center is of the circle. So there is the centripetal acceleration. Okay, so here's so ultracentrifuge can create accelerations greater than 1,000,000 times the acceleration due to gravity. Okay, by spinning it fast enough, the effective to make this stuff go around in a circle, you have to apply a force greater than 1,000,000 times gravity. That'll make all the stuff in there settle to the bottom real fast. Okay. So can create accelerations greater than 1,000,000 times the acceleration due to gravity, meaning that the body being centrifuge feels a force more than 1,000,000 times its weight. Okay, so to keep this object going in a circle, you have to apply a force 1,000,000 times greater than the weight. And so all the cells in a fluid, you cannot apply that force and they go and settle to the bottom of this tube. Okay? So here's the numbers, quick numbers. An ultracentrifuge spins at 150,000 revolutions per minute. And the material being centrifuged is 5 centimeters from the center of rotation. So this distance is 5 centimeters. 5 centimeters is 2 inches. Okay? And this thing is rotating 150,000 times a minute. Okay? So there is the acceleration the centripetal acceleration, and that is 1,000,000 times g. Okay? So that's essentially applying a force of 1,000,000 times g, 1,000,000 times its weight. And since the liquid cannot apply that force, all that stuff will settle down to the bottom, and then the bottom will apply that force. Okay. All right, so this shows you V is 150,000 revolutions per minute. And each revolution you travel that distance. Again, you don't have to remember all these, don't have to do all this. So this thing is traveling at 750 meters per second. That's twice the speed of sound. So in that ultracentrifuge, that tube is going at Mach 2. Okay. And the centripetal acceleration, you see this is 1.2 times 10 to the 7. 10 meters per second is g. So that's 1.23 times 10 to the 6 Gs. So a million times G. Yep. So that's the deal. That's what the centrifuge does. It'll make stuff settle down very fast by increasing G. Okay. All right, guys, that finishes this chapter.